Hey, hello, workshop students. I got a good question tonight that involves quite a bit more than just an answer by email or a couple pictures. And so I thought I would make a video, and of course, in the process of doing that, thought I would send it to all of you. But it has to do with the center of mass. So let me begin by talking about the center of mass in what we might call a discrete form. That is, if I had a grid that had an x and y axis, and then maybe I had a chunk of mass here and another chunk of mass here and maybe another chunk here. You might say this is, a triangle, if you will. But all the masses are at the points on the triangle, and so this mass, I'll call it M1, has a coordinates of x1, y1, and maybe this one we'll call it M2, has the coordinates of x2, y2, and then this one we'll call number 3, so it has a mass, and then has coordinates x3, y3. And so where is the center of mass? And we often call this a weighted average. There'd be two of them. There'd be the center of mass in the x-axis, and there would be a center of mass on the y-axis. Okay, now you do the center of mass by taking what, again, we would call a weighted average. You would take, in other words, mass number 1 and its x position. You would add it then to mass number 2 and its position. And then you would take number 3 and its position. Then you would divide that by its total. And so you could just say the total mass, the total mass. So you can add them all together. And kind of a shorthand way of writing that is to use the capital sigma notation, and then you can put your x sub I, your m sub I, and you would add up from I equaling 1, 2, and I'll just say n, because you never know how many you have. In my picture, I have 3. And then it just makes sense to just call this then total mass. And so that would be the formula in the simplest case. Now, I think your instructor proved to you why this is important. So let me not do that now, but let me take this one step further and say, well, what if it was a continuous object? And the question that we are asked to do, or maybe I should say you are asked to do, and so I'm trying to help you here, is to take something where the mass is spread out continuously in the form of a 45, 90 degree triangle. So a right triangle with 45 degrees. So a 45-degree right triangle. And so thinking of it in this way, you might say, well, how do I find the center of mass on the x-axis? And it's not just simply 3 points. And so what you would do is to say, well, imagine, chopping this into really, really thin strips where each strip has a value along the x-axis. And the problem we're about to do then has 1 meter for each of its legs. And so if I, again, cut this into a bunch of strips, you can see here that each strip has a new position x and has a smaller amount of mass because it's not as tall. And we're eventually going to get the the center of mass, what you would call a weighted average. You can kind of see the average. You're adding them up and then dividing by the total. Although it's a weighted average because you just don't add up the masses and divide by the total, or you don't really add up the position and divide by the total. You multiply it by a factor, and so things that have more mass carry more weight. And so it's not just an average position, it is a weighted average position, where the weight is based upon the mass of each piece, where something with more mass plays a bigger significant role. Like if this was the solar system, and maybe our first mass might be the sun, that plays the dominant role, even though there are other things like Jupiter would come in next and Saturn would come in next, and their position would be, some distance out. The position of the sun usually then dominates the overall center of mass. It's just such a big number. And that's what we're going to see here, except we're going to change this into calculus. So your author starts this problem with saying, know that then the x of the center of mass would be, and he gives you a little formula, 1 over the total mass. And I like to use a capital M. I noticed here that your author just gave you a little lowercase m, but if you'll let me change the notation, I'm going to put a capital M there, because that just kind of helps me know that I'm not talking about the mass of an individual piece, but the total mass. Although he does write total, so I don't think there's any point in confusion. But here is part of the question I got is, how did this summation kind of just disappear? And I guess I would say it didn't disappear. What happened is we imagined cutting this into thinner and thinner and thinner pieces. And so each piece has a mass, if I put this down here, of m, but I'm going to write it as a delta m, in the limit as delta m goes to 0. Now, it's still multiplied by its position, so there's the x, and then there is the summation, and that is the definition of an integral. And so the natural step, and I think why this might be a hard problem and why I kind of wanted to work it out, was to really talk about this equation, not just have you work through the equation, but to understand how it became an integral. And I hope this intermediate step helps with that, because you've been doing center of masses, or you were justified what the center of mass was based upon, of course, this really came from the sum of all the forces, which you might call the net force on a whole system, equals the mass of the whole system times the acceleration of the center of mass. And then you integrated it twice to get this. And I said I wasn't going to derive it, and I guess I won't derive it, but that's where this came from. Okay, and so once you understand the value of the center of mass, because the center of mass would be the place where when you add up all the forces, that's how the whole system behaves. The big step, I think, in this problem is then the conversion from making it discrete individual mass pieces, like 3 of them, into a continuous set of masses. And so changing this summation into an integration. And so I wanted you to see this first part and know where this came from. Because when you see where it comes from, I think you can understand a little bit better what we mean by the dm. So I'll say it again. The dm is this limit as the little pieces get thinner and thinner. I think you can also see what's bothering some of you is that, well, how do you do an integral with the dm? And the answer is you can't do an integral with a dm. So you have to do a change of variables to a dx to get the center of mass in the x, or change it to an integral with a dy in order to get the center of mass in the y direction. So there's still a lot of work to do in this problem. This is going to be a hard problem to do. There's no doubt about that. But the most important part of this problem is really understanding what do we mean by the dm, let alone then how do we convert a dm into a dx. That's still going to be a tough step here. And I hope I didn't spend too much time here babbling on about that. But again, this is an important idea of how do we change a sum into an integration. And then, of course, in the process, we begin to see what does dm actually mean. And then, of course, what does the x actually mean? And, of course, maybe the easier one is what does the total mass mean? Okay, so keeping that in mind, let's see if we can actually then do this problem. Okay, so the problem says to go ahead and define a grid so that the x and y axis make up the legs of a right triangle. So this is my right triangle, and it's supposed to be 1 meter in length. So this leg in the y-axis would be 1 meter, and this would be 1 meter. Which, what's going to come in play as we start to do the math then is this hypotenuse would be an equation of y equals, and if you remember our algebra, mx plus b, m is the slope, and b, of course, is the intercept, then y would equal to a negative 1x for the slope, and then plus 1 for the intercept, okay? So if I go ahead and I say, all right, let's figure out where the center of mass is along, say, the x direction here. I'm going to then chop this into pieces that look, I guess, like this. Okay. So now that you're kind of visualizing each of these, and I say, okay, where is the center of mass? I can say x of center of mass equals what? All right. Well, the first step is 1 over the total mass and an integral of, and so I'll come back here to page 1. It's the position of it. Okay, so I'm going to just kind of imagine starting with my first strip up against the y-axis, okay, and move on out, and so the x is going to be that value of that strip, and the dm is going to be the mass of each of those strips. Okay, well, so far I haven't done anything more than just copy this discussion here, but the big step now is how do I change a dm into, say, a dx? Because I can see that what I'm going to be doing is adding up strips starting here at, say, x equaling 0, and keep adding them up until I get to x equal to 1. And as I'm doing that, the strips get shorter and shorter, so the mass keeps changing. So there's some kind of connection here. And the key is the concept of density. See, density you can think of as a small piece of mass over a small little area. Or if it is something that has uniform density, and so this one does, then you can think of it as the total mass over the total area. I like to say, you know, if you're trying to get the density of a chocolate bar, you can take the whole mass of the chocolate bar and divide it by the total size of the chocolate bar. But you could also break it into those squares that many chocolate bars come in. And so take just one little square and get the mass of that small little square and divide it by the small little area. It's going to give you the same number. And so when we take advantage of that, we can then write a small mass by saying, well, let's think of the small mass as being one of these strips up here. And I'll just color this one in. And so I would say, well, that's my dm. And the area of this small strip, well, I guess that would be the height of it times its width. Now, since we're talking about a small little width, there's where the dx comes in. And then the height, I guess, would be the y along this line that's connecting them. And as I go further out, well, then this little piece over here has a smaller y. No, it has the same width. It's still a dx, but as we move out, it has less of a height. So this small little area would be its height, which I'm going to call y, and its thickness dx. See, and that's really what I want. That's the mathematical connection between the dm and the dx. And that's what I need to know to actually calculate this problem. Now, the other side of this is pretty easy. This would just be what we would call the total mass, okay, over the total area. And the total area is, you know, since this is a triangle, it's 1/2 times base times height. And height and base are each 1. So 1/2 base times height is 1/2. So this would be 0.5 square meters for the total area. Now, if you now move this over to here, you get what I'm hoping to get is dm by itself. And so it would be total mass over 0.5 meters squared, okay? Then there's the height of these strips, which is clearly a function of where you are on the x-axis. And then the dx. And then, if you'll let me go ahead and put what we said earlier, remember the height y is where you are on the x-axis. So in other words, if I am at x equals to 0, put in a 0 here and you get a height of 1. So that'd be this first strip. And then as I work out here, as x gets bigger and bigger, the height gets smaller and smaller. And eventually when x equals 1, the height is 0. So -1 plus 1 is 0. But I can replace that then with 1 minus x, if you let me just kind of change the order here. And then there's my dx. And that's kind of this magical step I needed in order to convert this into something that I can actually calculate. Because I'll say it again, this is a great way to write this equation when you're reading the math and you're trying to understand the physics behind it. It comes back to this little statement that you're just taking a weighted average. And so we like the dm. But when you go to actually do a calculation, you have to convert the dm into a dx. And so there is some factors that come into play, and that's what these are. As your math level increases, you'll learn to call this change of variables. And so when you are changing from a dm to a dx, oh, and I left out the original x, my bad. Okay. But so there's the original x. And then changing the dm to a dx, this extra factor I was beginning to say is called a Jacobian. So this is the Jacobian of transformation. and we transform it from a dm to a dx, we have to throw in this extra factor called the Jacobian. And of course now we can put up our limit saying we're going to integrate from 0 to 1. And now we can actually solve this. And the first thing is to notice that the mass total is both in the numerator and the denominator, so I'll cancel those off. This 0.5 I will bring in front of the integral. Maybe I'll multiply this x through so that it becomes an x minus an x squared dx. Still going from 0 to 1. Let me go to another page here. Then I have this 1 over 0.5 meters squared. And then, of course, this becomes an x squared over 2, and this becomes x cubed over 3, and each of them are evaluated from 0 to 1. So 1 over 0.5 square meters. And if you put in a 1, you get 1/2 minus 1/3. That's a common denominator of a 6, so that's a 3 minus a 2, so that's a 1/6. So it is 0.5 1/6, which I suppose you could just write this instead of 1 divided by 0.5 as a 2. So this is 2 over 6, where this is 1/3. So 1/3 of a meter is where the center of mass is. And if we come back to our original picture, that kind of makes sense. Part of this discussion on a weighted average was to say that the center of mass is not necessarily the center of the object. So the center of object being at 1/2, we can see that there is more mass to the left than to the right. So we kind of expect the center of mass to be a little to the left of this 1/2. Obviously greater than 0. So we expect it to between 0 and 1/2. And sure enough, coming up with 1/3. Where's 1/3? Seems very reasonable. Now, I was planning to do the y-axis, but I've talked quite a bit. And so I'm at 22.5 minutes here. So maybe I ought to take the clever way out and say, if you were dividing it in strips in the other direction, let me get a different color that might stand out. Maybe this blue will stand out. And I cut it into strips this way. Then back here when I did density, I would have dm over, and I would have then a dy here, and then I would have some kind of length along the x-axis. And of course, instead of having an x here, I would have a y. Instead of having an x here, I'd have a y. And I can go through and do the same math. But I think you're seeing that going up from y going 0 to 1 is identical to what I just did, which was going from 0 to 1 on the x-axis. So maybe you could kind of imagine taking this triangle. Maybe let's see if I can kind of show you, tear a little corner of a triangle. Oh, it's a terrible tear here. But if I took this triangle and I got 1/3, you could imagine if I were just to kind of flip it this way and now call this the y-axis, I would go 1/3. So what I would get is 1/3 up. So the center of mass is going to be really the same mathematics and really the same logic. And I wanted to show you that it still came out to be 1/3. But maybe in the interest of time, I'll just point out the symmetry of the x and y axis. And so it's going to come out to be 1/3. So where is the center of mass? So So if here's my grid, it would be 1/3 of a meter out and 1/3 of a meter up. And there would be the center of mass for a triangle, 1, 2, 3, that looks about, if I can try to draw it to scale, like that. And so that would be the center of mass. And of course we would care about that because now if I picked up this triangle and tossed it, the center of mass would follow the parabola due to gravity. That's the magical thing. So it's as if all the mass was at the center of mass, influenced by the external force of gravity. Or if we were in outer space and there was no gravity, then this center of mass, if I tossed it, would just continue in a straight line forever and ever. The other points would do circles around it. So if you wanted to know the motion of this point here, and you were in outer space, you could just say it circles around a constantly moving point. If we wanted to know the position of this point on the surface of the Earth, we would say it would be doing circles around a parabola. And so that center of mass is very, very important when it comes to our science and engineering. But this problem was about calculating it. So hope that helped. I'll shut it down for now. Take care.